lesson in physics, continuing our coverage of Unit 2, Measurement and Mathematics. Today, we're going to be talking about significant figures. The objectives of today's lesson are to explain the purpose of significant figures in a measurement, to relate the number of significant figures in a measurement to the instrument used to make the measurement, and finally, to perform calculations using measurements and express results in the proper number of significant figures. Significant figures are one way of properly handling the approximate nature of measurements. Remember, we've previously discussed how all measurements are estimations of a true value, an approximation of a true value. And that's a result of the gap between two graduations on a measuring instrument, whether it be a ruler or a triple beam balance, even electronic balances where we have digital scales. We don't know beyond the last digit what else might be there because the resolution of the instrument is limited. Significant figures also prevent us from overstating the precision of any results of calculations using measurements. Sometimes when we start multiplying things together, we end up with a lot more digits than we started out with. And some of those digits are going to be meaningful, others are not. Others are going to be filled with error due to estimation. And so we want to make sure that the results of our calculations have all the certain digits, but we only want to have one estimated digit in our calculation. So let's talk about identifying significant figures first. There are 4 rules for identifying significant figures. In any measurement that you see, all non-zero digits are significant. Also, all zeros between 2 non-zero digits are significant. And that doesn't matter how many zeros there are. As long as they're bookended by 2 non-zero digits, a non-zero digit on the left and a non-zero digit on the right, then those zeros are going to be significant. Leading zeros, zeros to the left of the first non-zero digit, are never significant. You'll encounter these when we're talking about numbers that are a fraction or have decimal places to the right of the decimal point. And so we might have 0.0053. Those first 3 zeros are leading. They come before the first non-zero digit. And so they are insignificant. They're insignificant because we could express the same number to the same precision using scientific notation. Finally, trailing zeros, zeros to the right of the last non-zero digit, are only significant if there is an explicit decimal point in the measurement. There has to be a decimal point written in there. The little dot has to be there. If it's not, any of those trailing zeros are not significant. They're there simply to provide placeholders so that the significant digits are given their proper value. And here we have some examples. So let's apply the rules for significant figures to these different numbers. In this first one, we can see that it's 1,012 centimeters. This number has 4 significant figures. The 1, and the 2 are all significant because they're non-zero values. The 0 is significant because it's between 2 non-zero digits. In the next one, we have 300.4 centimeters. Again, we have 2 non-zero digits, so those are significant. And we have 2 zeros, and the 2 zeros are also bracketed by non-zero digits. So once again, we have 4 sig figs. This next one, 0.0651 kilograms. These zeros coming to the left of the first non-zero digit are leading zeros. And as a result, they are not significant. They're not significant because we could rewrite this as 6.51 times 10 to the minus 2 kilograms without losing any precision. These zeros are simply to give the proper value to these, not increase the precision of our measurement. It doesn't give us any more digits to the right here. Instead, it just makes sure that we're properly interpreting these numbers. Because of that, leading zeros are always insignificant, not significant, and so this measurement only has 3 sig figs. In the next one, we have 8,100. These zeros are trailing zeros. They're to the right of the last non-zero number, digit. And because there's no decimal point here, these zeros are not significant. We could write this as 8.1 times 10 to the third kilometers, and that would express the number to the same precision that we've written here. Trailing zeros, when there's no decimal point, explicit decimal point written into the number, those zeros are not significant. And so here we only have 2 sig figs. The next number looks like the same measurement, but now we can see there's a decimal point after the last zero. A decimal point there, or a decimal point in the number, makes any trailing zero significant. So now this measurement has 4 significant figures. What this is saying is that this measurement right here, we used an instrument that was only graduated out to the thousands of kilometers, and we estimated the hundreds of kilometers. Since we can only have one estimated digit, this one right here, we put the zeros just to make us interpret this properly as 8,000 rather than 81. In this case, we were using an instrument that could measure out to the tens of kilometers, but estimate to the 1 kilometer. And so here, our estimated digit is in the ones place. All right, moving on to the next one. We've got some leading zeros. Those aren't significant. We've got the 3. We've got 2 trailing zeros. And because we've got the decimal point there, that means that those trailing zeros are significant. So we have 3 significant figures here. If we were to write this in scientific notation, we would write it as 3.00, so we have the proper number of significant figures, times 10 to the minus 2 meters. Next, we want to use significant figures in calculations. For addition and subtraction, answers are rounded to the place of greatest uncertainty, the estimated digit that is farthest to the left in the measurements being used. Here we've got a simple addition problem, 3.100 centimeters. This number has 4 significant figures, plus 2.91 centimeters, which only has 3 significant figures. Let's first just go ahead and add them together. So we have 0, and then 0 plus 1 is 1, 1 plus 9 is 10, carry the 1, 3 plus 2 is 5, plus 1 is 6. Remember that our rule is that we need to round to the place of greatest uncertainty. Here's our estimated digit there. Here's our estimated digit in that number. And so our place of greatest uncertainty is going to be the tenths. And so our answer can't be expressed any further than the tenths place. In fact, you can draw a dashed line like that next to the estimated digit that lies the furthest to the left. So our answer has to be rounded to the hundredths place. Our answer turns out to be 6.01 centimeters. Here the uncertainty is in the hundredths place. Here the uncertainty is in the tenths place. And so our answer will be rounded to the tenths place. And so we'll go ahead and put our dotted line in there. So we have 52.68 kilograms. And since this is an 8, we'll round up. So our answer will be 52.7 kilograms. Let's look at the subtraction over here. And so we're just going to go ahead and subtract. So our answer is 69.475. But now we have to express it in the right number of significant figures. To do that, we once again look, and we see that this one, its estimated digit is in the tenths place. This one's estimated digits is in the thousandths place. And we're going to draw our dotted line there. And so we have a 5 here, and according to our rounding convention, we're always going to round up on 5. So our answer will be 69.48 kilograms. Our estimated digit is in the hundredth spot, and that's because of our measurements, the most uncertain digit was in the hundredth spot. Our second rule is for using significant figures in calculations involving multiplication and division. And this one is actually a little bit easier. In this case, answers are rounded to the number of sig figs of the factor having the fewest sig figs. For instance, if you have two factors, one with 3 and one with 4 significant figures respectively, the answer obtained by multiplying them together or dividing one into the other would have to be rounded to 3 sig figs, because the factor with the fewest number of sig figs only had 3. Example, I want to show you how the estimated digits affect the results of the calculation. So I'm going to put all the digits that are affected by estimation in red and the ones that are certain in black. I sped this up so that you're not bored by me doing the arithmetic. The important thing here is that all the red digits are the ones that have been affected by estimation. So our answer, while it has 4 digits, has 3 digits that have been affected by estimation. And we can only have one that's affected by estimation. And so that would be the 3 here that will allow to stay. That's a 5, so using our rounding convention, we'll round up. So we get 44 meters squared. So our answer has 2 significant figures, which is the same number as the factor in the problem that has the fewest number of significant figures. That's a wrap on the lesson for significant figures. Join me next time when we continue Unit 2.